Pause the video and complete the quiz. Pause the video and check and correct your answers. Last lesson we looked at calculating the speed of an object given it travelling a certain distance in a certain time. We're going to do something very similar in this lesson, but we're going to use graphs instead of just numbers. This image shows 3 different containers and they've all got water in them. The first thing I want you to do is pause the video and describe the container. So, you might have said that container A has the same width all the way up. It has the same diameter, or you could even say it's got a uniform width or diameter. The word uniform just means the same or constant. Container B. Container B is in two sections. The first section has a wide, constant diameter or width. The second section has a much thinner but still constant width or diameter. Container C, the diameter or width changes as you go up. It gets wider, the diameter gets bigger, the width increases as you go up. I'd like you to imagine that water is being poured into each container at the same rate, so the same amount per second. And what I'm going to do is I'm going to show you some graphs. Now the graph on the y-axis has the height of water. So this isn't the amount of water, this is the height up the container. And on the bottom, on the x-axis, is time. So here are the 4 graphs. And what I'd like you to do is pause the video and see if you can match the container to the graph. Okay, so container A goes with graph 2. This is because the graph shows the height of water increases by the same amount for every bit of time, for every second. And this matches my description of the container because the container is uniform, it's the same width always, so the water is going to increase by the same height every second. Container B goes with graph 3. This is for a similar reason. The first section of container B, the wide section, increases at the same amount, the height of the water increases at the same amount per second, constantly, until the water gets to the second section. At that point, the water level increases at the same amount every second, but at a faster rate than it did before, because the second section is narrower. And container C goes with graph 1. This is because at the start, at the bottom of the cone shape of container C, the water level will increase very quickly. But as the container gets wider, the height of the water level will increase less quickly. And so you get this curve. The next graph I'm going to show you is a graph of the mass of a chocolate bar on the y-axis and time on the x-axis. So mass of the chocolate bar in kilograms on the y-axis and time on the x-axis. I'd like you to pause the video and see if you can work out what is happening. Tell me the story behind this graph. So the first thing I'm going to look at is that down here at 0 time, the chocolate bar has some mass, and that's the mass that it starts off as. And it stays at that mass for this amount of time, so about that much time. Now, something happens that means that the mass decreases. Now, I'm going to assume that someone has taken a bite. Someone's taken a bite out of that chocolate bar, and that means that the mass decreases. Now, there's another period of time here, between here and here, where the mass of the chocolate bar stays the same. That must be when they're chewing or something. And then here again, we've got the mass decreases. So this must be another bite. Then we've got a period of time where the mass stays the same. Nothing is happening to the mass, but time is still going on. So they must be using that time to do some chewing of the lovely chocolate bar. Then here, this is a massive decrease in mass. So I'm going to assume that that is an extra large bite. They must be really getting into the chocolate bar at this point. And here we have again a time where the mass doesn't change. So this must be more chewing. And here we have another change in mass. This must be a kind of regular size bite. That's a similar size bite to the ones we've had before. So a normal bite. And then a bit more chewing here where the mass doesn't change, but time is still going on. And at the end, we have quite a humongous bite again. And I know that's a bite because the mass of the chocolate bar decreases. Oops, that's an extra large bite again. And then here we have at the bottom the mass of the chocolate bar being 0 and time continues. So the mass of the chocolate bar is 0, the chocolate bar has been eaten. So we looked at a graph of height of water level on the y-axis and time on the x-axis. And we just had a look at the mass of a chocolate bar on the y-axis and time on the x-axis. Now it's quite common that time is on the x-axis of graphs like this. It's often interesting to look at how things change over a period of time. And that's what we're going to do next, but with distance that something travels. So we're going to have a look at a problem to start with and see if we can work out the distance that this person moves. So a person walks at a speed of 2 meters every second. 2 meters for every 1 second. So after 1 second, they will have moved 2 meters. After 2 seconds, the total distance, they'll have done another 2 meters, so their total distance will be 4 meters. After 3 seconds, they will have travelled 6 meters. After 4 seconds, they will have travelled 8 meters. After 5 seconds, they will have travelled 10 meters. And after 6 seconds, they will have travelled 12 meters. They go at 2 meters for every second that they walk. So I'm now going to plot the points onto this graph. Now this graph has distance in meters on the y-axis and time in seconds on the x-axis. So using the table before, after 1 second the person had gone 2 meters. So after 1 second they had gone 2 meters, so I've put a cross there. After 2 seconds they had gone 4 meters. After 3 seconds, they'd gone 6 meters. After 4 seconds, they'd gone 8 meters. After 5 seconds, they'd gone 10 meters. And after 6 seconds, they had gone 12 meters. Now what I've done is I've replaced those points with a line of best fit. And that's a line that goes straight through as many points on the graph as possible. So this is what you will see when you see a distance time graph. And we're going to have another look now at a different journey. So this time a person walks at a speed of 5 meters every second. So after 1 second they will have gone 5 meters. After 2 seconds, they will have gone another 5, so in total 10 seconds. After 3 seconds, they will have gone yet another 5, so 15 meters. After 4 seconds, 20 meters. After 5 seconds, 25 metres, and after 6 seconds, they'll have gone a total of 30 metres. So I'm now going to plot that data on this graph. So after 1 second, they had gone 5 metres. After 2 seconds, they had gone 10 metres. After 3 seconds, they had gone 15 metres. Now, unfortunately, this is where my graph is a bit too small. However, I'm going to draw a line of best fit and we'll have a look. So here we have the line of best fit, and I'm going to compare it now with the first graph we drew. So here you can see both the graphs from the first set of data and then the second set of data. The first one, I'll remind you, was walking at 2 metres per second, and the second one was walking at 5 metres per second. Now what we can see really clearly from these graphs is that if the line is steeper, then the person or object is moving faster. And by steeper, I mean for every 1 second, so for every, let's choose a colour, for every 1 second gone along this way, we compare how much their distance has changed. So for the red one, it's changed by 2 metres, but for the green one, it's changed by 5 metres. So without even doing any calculations, just by looking at the graph, I can see that the green one is moving faster because for every 1 second, they've gone further than the red one. Okay, let's have a look at another graph. So there are 2 sections to this graph. Section 1 that I've just put up and section 2. Now, there are a couple of interesting things we can do with this graph. The first thing is we could work out the speed of the object or person in this first section, so from down here to up here. Now, speed is how many metres something travels every second. So the first thing I would do is go across to 1 second and then go up and see how many metres that object has travelled in that 1 second, and they've gone 3 metres. Now let's have another look. After 2 seconds, so going across again to here and go up, leads us at 6 metres. So this object or person is moving 3 metres every second. 3 metres every second. And we can write that as 3 metres per second, like that. And that's for the first section, this section here. Now, the second section, from 4 seconds to 11 seconds, is here. This is interesting. This is a flat line. We haven't looked at this yet. Let's see what the speed of this object is here. So if I go from 4 to 5 seconds, say 4 to 5, the change in distance is 0. And so they're moving at 0 metres per second. This means that they're stood still. The object is not moving. So when you see a flat line on a distance time graph, we say that the object is not moving or is stationary. Pause the video and have a go at these questions. Pause the video to check and correct your answers. So the next thing we're going to do is we're going to describe a graph, but we're not going to use any numbers. So when we describe graphs, it's really useful to chunk them into their sections. So let's have a look. Here's section 1, here's section 2, and here's section 3 of this graph. So we're going to use words, not numbers, to describe what is happening in this journey. So, like I said, we're going to do this in sections. So from here to here is section 1. From here to here is section 2. And from here to the end here is section 3. Okay, so I can see, because there is a gradient, because this line is diagonal and not flat, I can see that this object has some speed. It's moving. So object. Now, given that I've told you that the steeper the line, the faster they're going, I would say this is quite a medium speed because it's a medium steepness. Okay, so the object is moving probably at a medium speed. We don't know any numbers, but that's not important at the moment. Section 2. Now I know that a flat line on a distance time graph means that the object is not moving. So the object is still. The object is not moving. Section 3, the object is moving again because there's a gradient. We can see that for a bit of time the distance is increasing. If I compare section 3 with section 1, I can see that section 3 the object is moving faster, and I know that because the line is steeper. So I can write object is moving faster than in section 1. And that's how to describe the journey using a distance time graph. Now you could always add a little bit of a story with this. You could say that a person was walking slowly to the shops. When they got to the shops, they stood still and then they ran home. And that implies that they're walking or moving at a medium speed to start with, then they're still, and then they move fast on the way home. So for each of these graphs, we've got graph 1, 2, 3, and 4. For each of these graphs, I would like you to describe the journey. Now, the first thing I did was section up the graph and describe what was going on. Then you could add a story to it afterwards if you want to. Pause this to check your answers, and if you came up with any creative story that goes along with this, that goes along with any of the graphs, then I would love to hear them. Next, I would like you to divide up your page into 4 sections, just like I've done here. And then you're going to draw a graph for each of these statements or each of these journeys. So pause the video and do that now. Okay, pause the video to check that you got a similar graph to these ones. Now, the length of time for each section doesn't really matter. It's the relative speed or the relative gradient that you're showing. Okay, the next thing we're going to do is we're going to use a distance time graph to find the speed of an object. So here we have a distance time graph. Distance is always on the y-axis and time always on the x-axis. And here's the line. So what we're going to do is very similar to last lesson. We need to find the distance and the time to be able to work out speed. So to find the total distance travelled, we go to the end of the line and we work backwards. You go that way along the line and you get to 60. So distance is 60 metres. Now the total time taken, we do the same, but we go down to the x-axis and we get 15 seconds. So time is 15 seconds. And we want to calculate speed. So the equation, speed is equal to distance divided by time. Speed is, in this case, 60 metres in 15 seconds. Now on a calculator, 60 divided by 15 is 4. So the speed is 4 and the unit is metres every second, or metres per second. So we're going to do a very similar thing for this one. The total distance, we go to the end of the line and go that way, is 80 metres. The total time taken is, if we look down, 5 seconds. And the speed is what we're looking for. So speed is equal to distance divided by time. Speed is 80 metres divided by 5 seconds. And that gives me a speed of 16 metres every second. Have a go at the worksheet distance time graphs so that you can practice calculating the speed using a distance time graph.